Hello everyone, I welcome you all for another video session on resonance. In the previous video we were discussing about series resonance and problem solving in series resonance. In this video we will discuss about parallel resonance. So before getting into the topic parallel resonance, let us see some of the basics. We know that the impedance of an RLC circuit is the combination of resistance and reactance, that is Z equal to R plus JX, where Z is the impedance and R is the resistance of the circuit and X is the reactance. So this is represented in rectangular form. We know that the vector quantities can be represented in rectangular form as well as polar form. So this is real part and this is imaginary part, so it is a rectangular form of representation. Now let me introduce three new terms called Y, G and B, where Y is the admittance, which is the reciprocal of impedance Z, so 1 by Z, and G is the conductance, which is the reciprocal of resistance R. We know that resistance opposes the flow of electrons. The opposite of resistance is conductance. It is the property of a material to assist the flow of electrons. And B is the susceptance, which is the reciprocal of reactance X. And this impedance formula can be written in terms of admittance, that is admittance is equal to G plus JB, conductance plus susceptance, and you can write it as Y is equal to 1 by Z, G equal to 1 by R and B equal to 1 by Z, and the unit of these three are ohms and the unit of these three is mho. Now let us move on to parallel resonance. The parallel resonance occurs when the inductive reactance is equal to capacitive reactance and the susceptance is equal to 0. So there are three different types of parallel circuits available for achieving the resonance condition. So one such circuit is this one. All the three passive elements are directly connected in parallel across a variable frequency supply. And the second one is tank circuit, which we have already discussed in series resonance topic, where R and L are in parallel with a capacitor. And another one is RL RC parallel circuit. Here the XL and XC are the inductive reactances and capacitive reactance respectively. Now let us derive the resonant frequency for the three different circuits. Let us consider a tank circuit. So the circuit is at resonance when the susceptance part of the admittance is 0. We know that Y is equal to G plus JB, where when B is equated to 0, at that time the resonance occur. So the total admittance of the circuit is this branch has an admittance of 1 by J minus JXC. That is, the impedance of this branch is minus JXC. The admittance is the reciprocal of the impedance, that is 1 by minus JXC. Similarly, the impedance of this branch is RL plus JXL. Hence, the admittance is 1 by RL plus JXL. Now, the total admittance is sum of these two admittances. Hence, 1 by RL plus JXL plus 1 by minus JXC. Now, if we do some simplifications, when minus J goes to the numerator, it becomes plus J, and we need to separate the real part and imaginary part so that the imaginary part can be equated to 0 to achieve the condition for resonance. Hence, in order to separate the real part and imaginary part, we need to multiply this term, multiply and divide this term by its conjugate. Therefore, the conjugate of this will be RL minus JXL. So multiply and divide. Here, since this is already an imaginary term, we need not do any further simplification. And let us see some basics. So using J term, when you multiply J into J, you get J square. The equivalent value for J square is minus 1. And similarly, J into minus J will be minus J square. So minus of minus 1 will be 1. And so on. So 1 by j can be written as minus j, and 1 by minus j can be written as j. So keeping this as basic, so here if you look at the denominator, it is of the form a plus b into a minus b. So the answer will be a square minus b square. So a equal to RL and b equal to JXL. Therefore, you will get is RL minus JXL divided by RL square plus XL square, because XL into XL will be XL square and J into J will be J square, which is minus 1, and in the formula itself there is a minus, so it becomes plus XL square. And now you can separate these terms, RL by RL square plus XL square minus JXL divided by RL square plus XL square plus J by XC. Now we have separated the imaginary term, so this is an entire real term. We don't bother about this real term, so consider these two terms, and for the simplification you take J outside, it becomes 1 by XC minus XL by RL square plus XL square. Now we are interested only in this term. This is of the form y is equal to g plus jb. So the coefficient of j is b, susceptance. Now in order to achieve this resonance, the susceptance part is equated to 0. So equate this term to 0. Yeah, so b is equated to 0, and 1 by xc can be written as omega c, and xl can be written as omega l. So take this term to the right hand side and omega will be cancelled. So bring c to the right hand side and take these terms to the left hand side. We will get this. So from this we are interested in finding this value of omega. From this we will find fr. So for finding omega, for the simplifications, so take this RL square to the right hand side and bring this L square to the right hand side. So omega will be equal to root of this term. Here L cancels, and omega can be written as 2 pi fr, where fr is the resonant frequency. So take 2 pi to the right hand side. So fr is equal to 1 by 2 pi into root of 1 by LC minus RL square by L square. This is the formula for calculating the resonant frequency of a tank circuit. Similarly, we can also derive the resonant frequency expression for this and this circuit. We will get these answers. So students, you can try this at home by following this tank circuit expressions. Now let us try to solve a problem based on parallel resonance. So consider this RL RC parallel circuit. So here for achieving the resonance condition, we need to find the value of L. So find the value of L at which the circuit resonates at a frequency of 1000 radian per second, where 1000 radian per second means the omega value is given. Sometimes they may give 1000 hertz or kilohertz, in which case it will be FR. Either FR or omega will be given. Okay. In order to solve this problem, let us write the admittance equation of this circuit. So we know that the impedance of this circuit is 12 minus J15. So admittance will be 1 by 12 minus J15. Here this is given as inductance in Henry. So let us write the reactance. So the reactance of this inductance is XL. Therefore admittance is equal to, so 1 by 12 minus J15 plus 1 by 7 plus JXL. The reactance is JXL. Now as usual, so we need to separate the real term and imaginary term. So multiply and divide both terms by their conjugates. So it is multiplied and divided by 12 plus J15, and this term is multiplied and divided by 7 minus JXL. And again this is A plus B into A minus B. Yeah, so this is A and J15 is B. So yeah, the total value is 369, and separate this into two terms, and again separate this into two terms. Now we have got two imaginary terms and two real terms. So we don't bother about these two real terms. We are interested in these two imaginary terms. Yeah, so how did we arrive at this 144 plus 225 is explained here. So A minus B into A plus B is equal to A square minus B square. It is 144. Here it is J15 into J15. We know that 15 into 15 is 225, and J square value is minus 1. So therefore it becomes plus 225. So the imaginary terms are brought to one side, and you take J outside, you get this value. And now we are interested in this susceptance only, the coefficient of J. So equate that into 0 for achieving the condition of resonance. And you need to simplify this expression for finding XL. So these are the steps followed for finding the value of XL. If you solve this quadratic equation, you will get two different values for XL. So one is 0.04384 ohms, and the second value is 0.456. Now we know that we are interested in finding the value of inductance L, but we found that found the values of XL, and we know that XL equal to 2 pi FL, which is equal to omega L. So in the problem, the value of omega is given. It is 1000 radian per second. So substituting this XL value and omega value, we can find two different values of inductance. Yeah, so I take the first XL value and use omega to be 1000. You will get L is equal to 43.84 microhenries. Similarly, when we use XL value to be 0.456, we will get L to be 456 microhenries. So this is how the value of L for achieving resonance conditions can be calculated. Thank you.